Bismillahirrahmanirrahim. My name is Mohammad Ehtisham and I am a research student of Institute of Space Technology, Department of Space Sciences. Today I am going to present my research work which is based on the EMRIs driven by supernova in the galactic center. Before going into the details of supernova and EMRIs event rates, first of all we will try to understand some basic concepts. Here comes the introduction. What are the gravitational waves? Gravitational waves are predicted by Einstein in 1915. It propagates with the speed of light. Gravitational waves can change the distance between two massive objects. Basically, it changes the space-time curvature. It has a small coupling constant almost equal to 10 power minus 45, which make them transparent, and hence there is almost no absorption and scattering throughout the universe. They have small amplitude, small effects. They are basically ideal tool to observe distant gravitational object, galactic centers, black hole, early universe. Sources of gravitational waves. If you look at the figure, there are two stellar objects and they make a binary with each other, and when they come closer to each other and pass through their nearby region, they basically propagate a pulse. And these stellar objects can either be neutron star binary system, black hole binary system, MBH with the white dwarfs, stellar remnants. There can be either of them. Here comes the LISA mission concept, that these are basically the three spacecraft constellation using the concept of interferometer, which is the Michelson interferometer, and it will be placed in a heliocentric orbit which will trail the Earth by 20 degree, by about 50 million kilometers. If you look at that red triangle, it clearly shows that it has an arm length of 5 million kilometer. We will not be going into the details of Michelson interferometer, but here is some basics about the LISA mission. It will fly in 2034. Here comes the extreme mass ratio and spirals. Extreme mass ratio and spirals are the gravitational wave sources induced when a supermassive black hole comes into binary with a compact object, which is clearly in the range of LISA, having the orbits of 10 power 4 to 10 power 5 orbits approximately. And why they are important is if we know the multipolar moments, and it can be found through the extreme mass ratio and spirals, we can easily detect the environment of a supermassive black hole. Supernova occurs when a star death occurs. When a star dies out, it explodes and only its core remains, and a huge amount of energy is being released. During that process, the compact objects might be scattered on an EMRI orbit. So it is basically a quite fertile region for emitting EMRIs. Here are some evidences from the past papers. There is a cluster which is called S cluster, having B stars, is a well-known area for the supernova kicks, and supernova kicks driving the EMRIs. For numerical approach, we do not use any analytical model here, because we know that these are extremely theoretical words. So that's why we use the Monte Carlo approach, that we know that supernova kicks has a velocity distribution in isotropic in nature, as compared to the Maxwellian velocity kicks that has a dispersion velocity of 265 kilometer per second. if we look at the graph, there are the relation between the eccentricity and the semi-major axis. They have come into this variation by using the Peters equation, which come from the post-Newtonian theory. They have used the Schwarzschild barrier, and here they comes into this point by using the clockwise S cluster. The probability that either supernova will induce an EMRI or not, we have this chart which clearly simulates everything. That is, we have started out from the initial eccentricity to the final eccentricity, which is quite lower in the initial stages, and in the final stages it goes into the higher orders. At the start, if we look at the graph, it clearly shows that there is no friction for EMRIs, but as long as we increase the eccentricity, it clearly shows that the eccentricity of this graph is 1. Here we conclude that the typical EMRI production timescale is of the order of million year, and they will be incomparable to the lifespan of massive stars and young stars in the galactic center. Assuming natural kicks of stellar black holes to be slower than those of neutron stars, our estimates suggest that 10% of MRIs in the Milky Way like galaxy